for coming, everyone. This is just a casual presentation on the steps we have taken to simulate a glacial climate with the ACCESS ESM 1.5 model. Let me just give a brief intro on why we are doing this basically. So the simulation is part of a big project where we are investigating the millennial scale abrupt climate events over Australia during the last glacial period. And that is a timeline between 32,000 years ago to 68,000 years ago. So what are these millennial scale events? These are some abrupt warming or cooling events, like Himadri event, during which there was a sudden decrease in Greenland temperature, shown here by green, and there was an abrupt rise in the Antarctic temperature, shown here with red. Surprisingly little is known about how these events affected the climate of Australia. And in this project, there's a team who is producing precisely dated reconstructions of rainfall and temperature trends in southern Australia around these regions. We have one record from New Zealand as well. These new terrestrial and ocean data will be compared with model simulations in order to determine how rapidly abrupt climate perturbations in the Northern Hemisphere reached Australia and the processes by which this occurred. These results will basically advance theory on how abrupt climate change propagates globally and would provide climatic context for events in Australia's natural history. In our project, we are targeting Himadri event 5, which occurred around 49,000 years ago, as this is the best time period considering our records, which are consistent for this particular time period. So to simulate the climate around 49,000 years ago, we are using these listed orbital parameters to fill in the values for eccentricity, obliquity, precision, which is used to get the executables to be put in the ACCESS model. We are using greenhouse gases from Kohler et al. So the CO2 at that time period is around 200 ppm, much lower compared to pre-industrial, which is 289. And then we have methane at 461 and nitrogen oxide at 231. The summer insolation for both the hemispheres at 49K compared to PI is higher during the summer. So this is, sorry. I want to go back. Can I? Yeah, okay. So this was the first step that we took. And then we implemented the ice sheet mask and vegetation in the model. We used the ice sheet reconstruction from Gowan et al. And what we did is we replaced the vegetation types in the northern high latitudes with the Laurentide and Scandinavian ice sheets. So removing tundra and then putting ice sheet over these regions. We also took some basic decisions like converting the needle leaf vegetation type into bare ground because between ice sheets we don't have any vegetation. And I will just point out that this is not done very randomly, but a close check has been kept with the Allen et al. Study, where they simulated the global vegetation pattern using the LPJ guess model in the last 140,000 years. We compared all these small decisions with this reconstruction as well. The simulation. And we also removed the C3 crops in the model from everywhere where they're dominant and divided its values to the next dominant types in that grid cell. So, for example, over India, the C3 crops are divided into C4 grass, and this green represents the broadleaf, I think. This is done in order to have the final sum of the total fraction of surface types as 1. This is important for the model, otherwise it crashes. So I just added this slide here just to put it out there that there is this problem of leap year in the ACCESS model, which is still not resolved, I think. I first had this issue when my model reached the 400th year, and yeah, we couldn't really figure out how to proceed with that. But a suggestion from Tilo, thanks, worked, which was to restart the counter from 1. So then, yeah, from 399th model year, I went back to 1, and then it worked fine. I didn't get this issue in the next 400th year. I don't know why, but I think this is still out there. So I have just posted this Hive link also here. Okay, so yeah, so lower sea level during glacial times and accumulation of fresh water, ice sheets leads to higher salinity in the ocean. At 49K, we are at about 44 meter lower sea level compared to present day. Following the PREMIP protocol, for this sea level, we needed a 0.33 PSU increase in our global salinity compared to the pre-industrial simulation. For this, what we did is we added a negative freshwater flux in the global ocean, which is following the methods of the freshwater simulations performed by Gabriel Pontes. But in our case, yeah, we applied this freshwater anomaly globally. The fourth step was to close the Bering Strait because, again, as the sea level was lower, there were some prominent straits and gateways which were closed at that time. We were running this simulation, but then I got this wall time exceeded error. And I think this is also something which is still out there. And I personally don't have a proper solution for it, but I know that some other people are struggling with this. And sometimes it works by deleting just the last restart and output files, but sometimes it also works if you just do PyU sweep and then PyU run again. But sometimes that wall time error just doesn't go. And I think I had one simulation where I just started my counter again just to have a workflow. Anyway, so the most important step was topography and orography. And thanks to David, who managed to create a setup to modify the whole topography at once for his Miocene simulations. And he helped us in adopting the same method for this experiment. We followed the topography also from Gowan et al. From there, we got the ice sheet. And just to show you the major changes that we did is that we closed the Hudson Bay area in our simulation. And we also closed the Sahul and Sunda shells as well as the Tasman gateway. Sorry. So yeah, just for reference, this was now our new modified vegetation and ice sheet mask, where we have ice sheet covered over the Hudson Bay area as well, and then some vegetation changes in this location. Yeah, we also implemented the river routine that David was using for his Miocene experiment. So we did this for our 49K time period. And looking at this, you'll feel that there were some minor differences between the two routines. However, in some places, for example, adopting the correct runoff, this one is the correct one, near the Bering Strait region led to the river flow toward the subarctic in the new configuration. Whereas in the old one, we were having a river flow inside, I mean, in the land and not over the ocean. This increase in river flow in the modified mask led to the decrease in salinity in this region, which further led to a decrease in our AMOC strength at 49K. So we kept the the modified river runoff and looked into how our AMOC and all the other variables would behave if we continue this run. So now if you look at the full-time evolution, this is surface air temperature, globally averaged, and southern hemisphere and northern hemisphere for all the simulations. The light blue here is the PI, and yeah, I have plotted the differences from the PI. The black is with the changes in orbital parameters and greenhouse gases. Orange is with the implementation of ice sheet, and green is with the salinity. Red is when we close the Bering Strait. And then we had the topography changes, which of course brought a big change in our climate. This is the topography one is the one that we ran the longest to get a quasi-equilibrium state. But then after implementing the runoff, we also extended this by quite a bit because as you can see, there's large variability still in the model. So the blue one is basically where I have the final changes. And if we zoom into the last 100 years of this blue time series, it looks more or less stable. So we are at a 3.8 degrees lower surface air temperature compared to PI globally. And for Northern Hemisphere, it goes by more than 6 degrees, basically. Same for SST, so there was a large variability in the simulations, and the last 100 years look okay. The global SST is about 1.1 degrees lower compared to PI, and yeah, we have, sorry, this is Northern Hemisphere, not Southern. And yeah, it basically the idea is the last 100 years look pretty much at a quasi-equilibrium state. Yeah, so the AMOC time series also varied by quite a bit. And also I would like to point out that we have quite a bit of like very strong AMOC in this 49K simulation. I'm not sure why, I think this model has a very strong AMOC at a glacial climate. And if I look at the last 100 years, then it stabilizes to around 30 months sword drop, which is quite high compared to the glacial simulations that have been performed with other models. For sea ice time series, yes, let's just focus on the full evolution of the southern sea ice. We see some increase compared to pre-industrial, but with large variability, of course. And for northern sea ice, I would just show the topography and the runoff one because the ones previous, the ones which are for the previous simulation, the Bering and salinity, they have different ocean and land points. So at the moment, it was not comparable. I mean, I'm still working on getting a calculation which can get me the whole time series and we can compare apples with apples. So that's work under progress. But then, yeah, the last 100 years for this blue time series again look quite okay, I would say. Yeah, finally, the plots here show the globally average salinity and ocean temperature. We were adding salinity continuously, so we have such a huge linear increase all the time. Global ocean temperature is about 1 degree lower compared to PI. And yeah, it's still increasing, but that's a very less yeah, change. So this is where we have basically stopped right now. And yeah, this is just some initial analysis that I'm currently doing. So this is surface air temperature anomalies at 49K. So the last experiment in the last 100 years of that experiment compared to PI. As you can see, it's significantly colder. We have quite a bit of strong AMOC, so there is increase in the temperature in the North Atlantic. This increase over here is just because we converted a lot of ocean points into land. And yeah, the whole role of specific heat capacity plays in there. In terms of precipitation, there seems to be a southward shift of the ITCZ. I'm still analyzing this more carefully. And for SST, sorry about the change of the domain. But yeah, so with strong AMOC, we have such a high increase in SST in the North Atlantic area. And yeah, like I said, I'm still analyzing it. And I would yeah, really like your feedback on what we can look at in this simulation or what we should be careful about. In terms of Australia, yeah, I just wanted to put the slide out there. So like this basically shows us that at 49K, we have increased rainfall in the northern part of Australia with a decreased rainfall in the southern part of Australia if we consider the monsoon season. But for JJA, we mostly have drier conditions. Yeah, like I said, I'm still analyzing this, everything. And I think this is where I would stop at the moment. But just to mention, yeah, so the next step would be to perform a freshwater simulation from this 49K equilibrium state, which will be done by Yan Xuan Du from University of Melbourne. And then we will assess further how the Australian climate change under millennial scale climate events. Thank you.
Thanks, Himadri. Any questions?
Can I go for a question, Tilo?
Yeah, please.
Sure. So that's great, Himadri, and it's very nice to see those simulations reaching some final equilibrium at the 49K climate. I was just wondering about your ITCZ shifts that you were looking at. And for me, it seems that there was a northward ITCZ shift. And this is quite expected from the results that you've got for the AMOC. So when you've got even stronger AMOC, this enhances the heat transport to the northern hemisphere. And you'd expect a northward ITCZ in order to counterbalance the fluxes, the heat fluxes between the northern and southern hemisphere. But of course, you were also doing like great changes in the ice sheets, and this could also have an impact. But yeah, I think it's a nice thing to look at, and it could get like great insights of the ITCZ dynamics and also how it impacts the Australian rainfall by looking at those processes.
Thanks, Gabriel. Yes, that's a good point to note. I will look into it. Yeah, thank you.
Yeah, it was more like a comment than a question. Sorry.
It's okay.
David.
Yeah, thanks, Himadri. I was just wondering, because we do see some pretty large changes in precipitation in that northern Australian region. Do we have much proxy information? I know that you're thinking about southern Australian proxies, but are there proxies for northern Australia and that whole kind of new land area that we've exposed as to what's going on with precipitation?
Yeah, so we do have some proxy reconstruction from like old papers. And they do cover this timeline as well. But the problem is that some of these proxy records show like whatever change they are showing, they could be during an Henry event. So it's hard to really find, what do you call it? Sorry, I don't get words, but it's hard to find the resolution, which time period they are talking about, basically. But there are proxy records for Northern Australia as well as the Indian Ocean part. So yes, I mean, as we have closed this part, it will be really interesting to compare our results with the proxy reconstructions and see if there is any dynamic play there, which we are getting in our model simulations, and what was the interpretation from the proxy records. Yeah.
Thanks. Joe?
Yeah, really interesting. Like, I just wondered if you had thoughts on why ACCESS ESM has such a large strengthening of the AMOC in the glacial climate compared to other models.
Yeah, that's a good question, Joe. I'm not sure I have the answer right now, but this is something that I'm going to analyze further, that why we have such a strong AMOC. Yeah.
So it's a bit more extreme than what other glacial simulations have found?
It is, yes.
Yeah.
It is, yes. So 31 sword drop is actually out of the range of the AMOC strength that we have found in our model simulations. One thing, the first thing, I expected is because we are introducing a very strong cooling, actually. So that could be one of the effect. 200 ppm is fine because we have those kind of, CO2 concentrations, and AMOX is still around between 11 sword drop to 19 sword drop during glacial climate. So my first guess would be that we are introducing a very strong cooling in this model. But yeah, that's something that I have to figure out why we have such a strong AMOC.
Interesting, thanks.
She won't. I think we lost you, Siobhan. Yes.
Okay, yes. Yeah, I guess my comments are also about the AMOC and the sea ice in the Labrador Sea, which is obviously closely linked. It looks like the sea ice has disappeared there, so that's why the SST and temperatures have increased. And also what's happening in the Bering Sea area, where you've shut the land bridge there, which means in the summer that the you don't need to put the Bering Sea one up. Just so you've got the freshwater flux and runoff there, which is a little strange, but I'd have to go and look in detail what was happening there. But if you go back to that SST and temperature plots that you had, for the globe, yeah, so this one. So you've got air temperature increasing when in the summer, so the land is now much warmer, but you've also got the ice and the ice in the pre-industrial, which makes sense because normally it wouldn't really be treating until August and September in that region in the ESM 1.5. And again, you've also got the ice retreating. The ice is retreated in the Labrador Sea, which is an area where you've got potential convection, and that's next. So that could be what's driving it. But it's sort of strange when you've got such a cold continent that you've got this ice retreat going on, which is why I'm a bit surprised. So yeah, that would be one reason why I'd be looking carefully at why, with the strong cooling, that you've still got ice retreat going on as well. So it's sort of counterintuitive, as Joe has said, why in the glacial climate you've got an increase in AMOC. So there's various things to look at. Obviously, there's the salinity. You've taken water out, so the salinity is increased. So the salinity of that over that area and the cooling are both going to drive an increase in AMOC, but the sea ice properties won't be driving it. So it's counterintuitive.
Yeah, I agree with you, and I'm sorry I don't have the sea ice plot here, but yeah, I mean I'll look at the sea ice as well in this one. Yeah, I'm having some trouble in plotting sea ice. Yeah. Okay, I'll keep this in mind.
Yeah.
Thank you, Siobhan.
Thank you.
Any other questions? If not, then thanks again, Himadri, for your talk.
Thank you, everyone.